Okay, question number 12 on nuclear fusion. Calculate the electrostatic energy between two protons that are separated by 10 to the minus 5 meters. So the energy is U is K, Q1, Q2 divided by R. So K here is the Coulomb constant, 9 times 10 to the 9. Newton meter squared per Coulomb squared. Each of the protons is 1.6 times 10 to the minus 19 coulombs. I'm going to square that. And then divide by the separation, 10 to the minus 15 meters. And if we calculate all that up, we get that the potential energy is 2.3 times 10 to the minus 13 joules. At what temperature would protons have enough kinetic energy to overcome the Coulomb barrier so that the nuclear force can take over? So for this, we want to do average kinetic energy is 3/2 kT and solve for T. This is a different K, of course, but if we get T by itself, it's 2/3 K over little k. Okay, and if I plug that in, I get approximately 1.1 times 10 to the 10 Kelvin. So we're going to put our energy in here. And then, do I have my concealer? Yeah, so we're going to use our Boltzmann constant here. 0.3 times 10 to the minus 23 joules per Kelvin. Okay, so now we're up to the last part. So temperature in the core of the sun is 10 to the 7. Is it hot enough for fusion to occur? No, it is not, based on just this classical idea that you have to have enough kinetic energy to overcome the Coulomb barrier. So T core is less than T fusion. So fusion could not occur. Without the quantum mechanical effect of tunneling. Okay, this is a biggie. Okay, sketch the evolution of a one mass solar mass star on the HR diagram. And then on your diagram, indicate the zero made sequence. Okay, so let's get our HR diagram here. We have temperature increasing to the left. And then we have luminosity increasing this way. Okay, and we have like the basic, main sequence, like so. Okay, so the sun is going to start on, we're just talking about the 0 main sequence, so that's part 1. It's going to go to the red giant, so it's got to move. Remember, this is also temperature, it's also color, so we have red here, blue here. So it's going to move toward the red and also increase in luminosity for the red giant. So that's 2. And then it's going to go to the horizontal branch. And this way. That's 3. The asymptotic branch goes up like this. So that's 4. Planetary nebula will happen here. So that's our 5. And then white dwarf. It will come down over here somewhere, and then it just cools and fades. So this is 6, or VI. Okay. Indicate the star's primary source of energy and what drives its motion on the HR diagram for each of those phases. So 1, we have, so step 1 is the main sequence. and we have hydrogen going to helium in the core. Step 2 is the red giant phase. So red giant, we have an inert core, so nothing's happening there. It's just a core full of helium. And then we have a shell surrounding that, so hydrogen going to helium in a shell. And that puffs up the star. So that increases its luminosity, but also drops its temperature, surface temperature. Okay, then suddenly gets hot enough for helium fusion to ignite, and we go into the horizontal branch. So in this case, we have helium going to carbon in the core, and probably still a little shell of hydrogen going to helium. Okay, and then it's basically like a mini second main sequence where that's, fairly stable reaction. And then we have phase 4 is the AGB, asymptotic giant branch. And this is analogous to the red giant. So we have an inert core again. So this time there'd be carbon in the core. And then we'd have a shell of helium going to carbon in a shell. And then hydrogen going to helium and even another shell outside of that. Oops. Put the E in the wrong one. And you get, I forgot to say this is like more stable. So the size decreases and the luminosity decreases. Okay. So in this case, our size, because it's basically blowing up as a giant again, so our size increases, the luminosity increases. The effective temperature gets a little bit redder there. And then star's energy, 1, 2, 3, 4, and 6. So when we are in 6, there is no energy. So the white dwarf phase, it's just cooling due to hot temperature. So we have, electron degeneracy that's supporting the star. Okay. These two. Oh yeah, we can do this one quick. Okay, so the equations of stellar structure describe how pressure, mass, temperature, energy production vary with the radius of the star. So these are differential equations that must be solved numerically. Describe how numerical iteration proceeds in a very general sense. So for example, if you know the conditions at the center of the star, what's the next computational step? So we talked about this where you basically, it's like an Euler type solution where you just would break the star into concentric rings, right? So we could just say like this is I and this is I plus 1. So if we know the conditions in the center, then we can figure out what they are in the outside. So the temperature in the next outer zone of I plus 1 is going to be the temperature in the inner zone, Ti, plus dTdr times dr. So it's just kind of like an Euler way of thinking about it, right? And you could say the luminosity in the outer shell is luminosity in the inner shell, plus the equation for how luminosity changes with radius, plus our step delta r. We'll make that a delta r. And then same thing for the mass. If you want to know what the mass is in I plus 1, it's the mass in the inner shell, plus some description of how mass changes with radius, plus delta r.